Now we'll start grand canonical system in statistical mechanics. What is grand canonical system? It is the collection of the large number of identical system or copies in which both energy and particle can be exchanged among the members of the ensemble. In the ensemble, their energy and number of particle can be exchanged. So this is grand canonical ensemble. Now we consider an ensemble of n identical system. We consider this is a n identical system will be there. Okay, n1 of this system, here total system is n, identical system is there, and n1 of this system in state 1 with energy E1 and the number of particles n1 at any time. N is the total identical system will be there, and we find like n1 is system in state 1 and the energy in this state in this system is E1 at any time. If Ni of this system with energy Ei and the number of particles Ni at any instant of time. So this is in I state. Okay, so this is one state, and this is, if we consider I state energy is Ei and number of particle is Ni. In grand canonical system there have some condition is summation of Ni is n. So Ni is the total number of system, summation of Ni is total number of system, and this is capital N. Okay, and summation of Ni and capital Ni equals to n into n average. Here n is total number of system and n average is the average number of particle in this system. Okay, so summation of small ni into ei equals to n into e average. Capital N is total number of the system and e average is average energy of the system. Now we consider any set like Ni is a set of members of the numbers in Ni which satisfy the restrictive condition. Okay, this is condition we consider for grand canonical. This follow this set. Okay, so one equation will be summation of Ni equals to n, summation of Ni into capital Ni equals to n into n average, and summation of Ni Ei equals to n into e average. So this is the condition. Okay, this is the number one condition. This equation is number one consider. Equation represent one of the possible modes of distribution of particle and energy among the member of the ensemble. Now, n1 systems are to be accommodated in state 1 out of the total number of n system. So we just consider n1 system out of the total number of n system. Okay, since the systems are indistinguishable mean system can be find out differently. Okay, so the number of possible ways of choosing n1 system out of n system. n1 system out of n system equals to n factorial by ni factorial into n minus n1 factorial. Okay, so this is n1 equals to n factorial by n1 factorial into n minus n1 factorial. First we find n1 system and now we'll find n2 system. So thus n2 systems are to be chosen from n minus n1 because n system is total system and now is n minus n1 system will there. Okay, so we find out n2 system from n minus n1 system. So thus n2 systems are to be chosen from n minus n1 system. So this can be denoted in n minus n1 cn2. So n minus n1 cn2 is equals to n minus n1 factorial by n2 factorial into n minus n1 minus n2 factorial ways. Now, since these systems are indistinguishable, okay, the total number of possible ways is n factorial by n1 factorial into n minus n1 factorial into n minus n1 factorial by n2 factorial n minus n1 minus n2 factorial. Okay, so this is n1. So now this will be this cancel out and same as the term will be cancel out. So this n factorial by n1 factorial, for this term there will be n2 factorial and another there will be n3 factorial. So the probability of obtaining such distribution is omega equals to 1 by c n factorial by n1 factorial, n2 factorial into n3 factorial and dot dot dot. Okay, so this will be n factorial by c into pi I ni factorial. Okay, so here c is the total number of possible distribution. Most probable distribution in the one for which omega is maximum. So here omega equals to 1 by c into n factorial by n1 factorial, n2 factorial dot dot dot. So ln omega equals to ln n factorial minus ln n I factorial minus ln c factorial. So this term, so this is this term. For grand canonical system, this n is huge, this n is like infinity. So we can apply here Stirling approximation. N ln n minus ni ln n I minus ni, but there is a minus, this is constant term. So this is, there no approximation will be applicable here. Now this is n ln n minus ni ln ni plus summation of ni minus ln c. For W to be maximum, this omega to be maximum, we will find that delta ln omega equals to 0. This is maximum condition. So and ln omega is this. Now n ln n minus ni, summation sign will be there. Ni ln ni plus summation of ni minus ln c. Delta ln omega will be there. Delta of n ln n minus ln delta n minus delta of summation of ni ln ni plus delta summation of ni minus delta ln c. This is constant term, this is constant term, this is cancel out, and here n is constant, total number of system, and summation of ni from this grand canonical ensemble, their condition, this summation of ni is capital N. So this is also total number of system, this is also be constant, so this also we cancel out. Okay, this cancel out. Next n is constant here, so delta n is also cancel out. Okay, so now the term will be delta summation of ni ln ni. So this will be 0 from maximum condition, and delta summation of ni ln ni equals to 0. Ni into 1 by ni delta ni plus delta summation of ni into ln ni equals to 0. This term cancel out, so this is 1 plus ln ni into delta ni equals to 0. Okay, so this is the total term. Summation of 1 plus ln ni delta ni equals to 0. From equation 1, so these are the equations. Summation of ni equals to n, summation of ni capital Ni equals to n into n average, summation of ni into ei equals to n into e average. Now summation of delta ni equals to 0 because n is total number of system. Summation of ni equals to n, and this is total number of system. This is constant. So for constant, and derivative will be 0. Also summation of ni delta ni equals to 0, and summation of ei delta ni equals to 0. Now multiplying Lagrange's multipliers gamma, alpha, beta respectively, and adding to the equation 2. equation 2, this is equation, this is equation 2. Okay, this is equation 2. Now summation of ln ni plus 1 plus gamma plus alpha ni plus beta ei delta ni equals to 0 for any arbitrary delta ni, because delta ni cannot be delta ni not equals to 0. This term will be 0. Then ln ni equals to minus 1 plus gamma minus alpha ni minus beta ei. Now ni equals to e to the power minus 1 plus gamma minus alpha ni minus beta ei. Okay. So this is a system number. This is a system of ni in ith system. Okay. So summation of ni is capital N, total number of system. So this is e to the power minus 1 plus gamma into summation of e to the power minus alpha ni minus beta a, and e to the power minus 1 plus gamma equals to n by summation of e to the power minus alpha into ni minus beta into a. So ni by capital N equals to e to the power minus alpha ni minus beta ei by n minus summation of n e to the power minus alpha ni minus beta ei to this, and ni by n is the probability distribution function. Okay, this is the probability of finding the system in state I. So this is the probability of finding the system in state I mean grand canonical ensemble. Okay.